Nobody in the world except a select few know what I'm going to tell you in this section. I myself stumbled into it in the course of doing research for this chapter of my book. I never imagined that such a world that I'm going to expose to you existed, but now that I do, I am gloating with immense latent but potential power within me. As a writer, this yet hidden knowledge that I have uncovered is a gold mine. For you, it might be just something interesting. However, if you are related to research and you have a very inquisitive mind, this section will also lead you to the gold mine that I have found. Without looking for it, I stumbled at a confluence. There were 4 rivers flowing into a single place, and the resultant river, as you can imagine, was gigantic in proportion. It was fascinating. I never knew such a thing existed, at least not in the world of knowledge. In the world of sports, such confluences are not uncommon, and among them, one sport fills me with excitement every time I watch it. It's MMA, or mixed martial arts. It is such an exciting sport because it's the confluence of 4 martial arts. They are Brazilian Jiu-Jitsu, Thai boxing, conventional boxing, and wrestling. All the rules are twisted, broken, and all hell is loose in MMA. Because of this confluence, this sport offers immense thrill. As you must have guessed, I'm not here to talk about MMA, but it's just a prelude to introduce you to advanced modeling and data analytics, or applied statistics. This topic, despite its boring long name, is that near magical confluence that I stumbled upon in my earlier research. Applied statistics is where 4 disciplines converge. The first one is the one we just learned about earlier, that is inferential statistics. It provides the core logic to applied statistics. The second river is the mathematical foundations, which provides the reliability. The third discipline or subject is computational science or computer science, which enables the execution. Then the fourth river is data visualization, which enables the communication of the results. You won't be impressed by this analogy yet, and if you are not impressed, then you will not be able to see this gold mine that I'm seeing. The reason the old pedagogy failed at creating large numbers of researchers is that it never bothered to impress the millions of wannabes could have been researchers. So despite seeing the gold mine, they did not know what to do about it. Then they just left research and took on a procedural job. They did not have to earn a PhD through their research, but they could have made businesses, movements, or a simple happy family based on research. But my four-brain learning approach would rather forsake the breadth and depth coverage of a subject to ensure the student sees the gold mine for what it is and is baffled, swept away, enamored by the subject, its implication and its application. So let me begin to inspire you into applied statistics. Do you remember when you were young and the teacher would provide you with IQ tests? You can still do that on your own by going online if you have not been exposed to them yet. You'd be provided a series of numbers or items, and you would be asked to find out what the next number or item in the series would be. For example, you would be given a sequence like 1, 3, 5, 7. What's the fifth number going to be? So the idea is if you are intelligent enough, that is, if your intelligence quotient is high enough, you'd be able to find the rule that governs this sequence. For this particular one, it's a simple one. The rule is just to add 2 to the previous number, so the next number will be 9. Then let's look at another example. Let's say a sequence is 10, 5, 8, 4, 7. So what's the sixth number? This requires more IQ. You would need to rack your brain a bit more to find the rule, which is subtract 5 then add 3. When you do that, the next number becomes 3.5, but it doesn't make sense. So your IQ would have to revise the rule, and by working your circuits over time, you realize that the revised rule is divide by 2 and then add 3, and the answer is still 3.5. So it must be the correct one. Even by reading the problem, the solution and the answer, your head was already spinning. Now what I am trying to tell you is that applied statistics is the tool that gives you the highest possible IQ score of 300, and it's legal. So am I catching your attention now? For applied statistics, the sequence is what we call the input or X features, and the next number is the outcome that we want to predict. Then the rules that we discovered is the predictive model. As I already mentioned to you, applied statistics is the confluence of the four disciplines we discussed. So now computers combined with mathematics and statistics find out the rule that we took so long early on to find out within seconds. Isn't that amazing? So you are slowly feeling the gravity of applied statistics. But my next example will seal the deal for you. We all know of Einstein. He was famous for challenging Newton, but I'm not going to talk about either of them. I won't talk about Kepler, on whose work the two scientists I mentioned depended. Before Kepler, the understanding was the orbits were circular. Of course, now we know they are elliptical. What we do not know is how we have come to this obvious conclusion. The mentor of Kepler, Tycho Brahe, provided him with extensive astronomical data showing the motion of Mars around the Sun. So that was the X feature or input variable. Kepler wanted to predict where a planet would be when. So this is very similar to our earlier IQ test with the various sequence of numbers. The data containing the position of Mars at various points in time are the numbers in that sequence. The next number is the position and time the planet would be. So Kepler, like our student trying to solve the IQ test, racked his brain to find out the perfect rule or equation that matched the data that he had with the data that he wanted to find out. He tried everything from geometry to trigonometry. Every time he thought that he had the correct next number or position and timing of the planet, there was an error of 8 minutes. After 10 years of trying to find the correct equation or predictive model, he found it. The error disappeared if instead of a circle, the ellipse was used. So a new set of formulas and rules had to be developed. Now that took him a decade, can you imagine? Applied statistics today, with this advanced modeling and data analytics, after being fed clean data of the orbit of Mars around the Sun, would have produced Kepler's first law within a few minutes. Just imagine what the implication of this gold mine can be. With this kind of technology and the confluence of knowledge, a person like Kepler could have solved thousands of more problems and made humanity still much better off than it is today. But let's forget Kepler because he's long dead. Just imagine the application of applied statistics to you, the future Kepler or potential Kepler. What could you do after discovering this confluence with so much power? You could make discoveries that are not only revolutionary but that will make you billions. So now that you are impressed and inspired enough, let me get into the actual exposition of applied statistics. As usual, I'll be referring to the diagram below, and so can you. First, take a look at the Venn diagram. It shows the relationship between the four components of applied statistics. The whole universal set can be called as data science, and then there are three sets. The first one is data mining. You will recall that we slightly brushed on them in the earlier section. Then the second set is the time series analysis. Then the third set is the predictive modeling. The Venn diagram shows how they are interrelated. Data mining can be done on its own, so can predictive modeling be done on its own. However, time series analysis is a subset of predictive modeling. There are some predictive modeling that intersect with data mining, and then there are some that intersect with time series analysis also. So now you have the big picture of applied statistics. Next, let's look at the 5 steps of predictive statistics or applied statistics. I will first describe the process and then provide examples to illustrate it so that it's easier for you to retain the information. Although applied statistics is part of statistics, you must remember that it's like MMA, and inferential statistics is like Jiu-Jitsu. The later answer the question like are these two data sets or variables related? Is their relationship significant or non-random? How much change in one unit causes how much change in the other variable? That was very simple, like Brazilian Jiu-Jitsu. But applied statistics is at a totally new level. It doesn't care if there is an established relationship between two variables or more. In fact, it even doesn't care how many variables you are considering. It can take in trillions of X factors. What applied statistics answers to is the question, based on certain input or X features, what do you predict will be the next number or category or sequence? it doesn't even bother to check if there is a relationship between the X factors that are being inputted. Applied statistics will find any kind of linear or non-linear multivariate relationship or equation that matches the training data to the closest fit in order to produce any output. There will be error, and that's okay. It will be fed back as a training data into the predictive model so that it can tinker its weightage and mathematics to produce an outcome for a new test with less error. And this goes on continuously until error is small enough. So the first step is to define the problem. Here we clearly state the specific outcome to be predicted, then determine the necessary data type. It can be numerical, categorical, or sequence. The second step is to collect and process the data. Here we gather the data, clean it, handle the missing values, and engineer the X features or variables. The third step is to build the model. That's the mathematical and computational part. We select the appropriate algorithm. It could be regression, like we used in inferential statistics, or more complex like classification and LLM. Then we'll train this model on historical data. The fourth step is to evaluate the model. So we'll test the model's performance on unseen data. It means we know the input variable, but we don't know the predictive value. At least the model doesn't know. Then we also select the appropriate metric to measure the error. It can be R square, F1 score, or simply accuracy. Finally, the fifth step is to deploy and monitor. We implement the model to make live predictions. Then we continuously check for performance decay or model drift. Now let's apply this five-step process to the financial market. Step 1, our goal is to predict the categorical direction, up, down, flat, of the S&P 500 index over the next 30 days. Our step 2 is data mining. So we collect stock prices, volumes, economic reports, social media sentiment. Then you use the data mining to clean the noisy and extract features like volatility index or sentiment score. In step 3, we build a model, and in this case it's the time series analysis model. Step 4 is we evaluate it to ensure that the model is correctly classifies the up and down movement that we are seeking more often than a random chance. And in step 5 we just deploy the model and we feed the up and down predictions into a trading algorithm which make the decisions. Again, you don't have to understand everything that you read here. The idea is to understand the big picture and understand the pattern. Now a very simple, relatable use of applied statistics, which might seem doesn't exist but actually exists in many big organizations. It is the likelihood of getting a promotion. So the goal is to predict the probability 0 to 1. This is a number, as opposed to earlier where it was a categorical direction, that is up, down or flat. So we want to predict the probability that a specific employee will be promoted within the next 12 months. Step 2, in order to collect data, we do data mining. We collect the employees' performance reviews, tenure, department, project, success rate, and training history. We use the data mining to normalize scores and encode categorical variables. For example, department A is equal to 1. The computer understands numbers, not categories. That's why you have to do that. Then we have to choose the model that best fits our objective. For this one, the random forest classifier model, to weigh the importance of various variables like manager rating versus tenure to classify employees as a promote or no promote would be the most suitable. Then in step 4, we evaluate the model, and then we deploy it. The model runs quarterly, generating a probability score for HR review. If the model's accuracy drops below threshold, the model is retrained on the newest data. So isn't it a gold mine, this applied statistics? The confluence of 4 powerful disciplines leading us to infinite research possibilities. With the knowledge and technology of applied statistics, we can predict anything that we can set a goal to, or do the step number 1 for, which is to define the problem. So this takes us to the next part of the big picture of applied statistics. Along with me, please refer to the 2x2 matrix in the diagram. The first box consists of problems that we want to predict, which are of the high chaos and high stake nature. It means that these problems have got lots of variables at play. Don't worry, we will explore the examples later on. This is what high chaos means. What high stake means is that the problems in this quadrant are very important or mission critical. It simply means that a small error in the prediction can be catastrophic. So the prediction focus here is non-linear, unpredictable events where error cannot be tolerated basically. It can be pandemics, stock crashes, geopolitical conflicts. You must recall the predictions by WHO or World Health Organization that told us at what rate the coronavirus would be spreading, and how many of us would be infected by when, and how the number would change if we were vaccinated and we use various type of preventive measures or curative measures. The type and number of X factors in this type of problem are emergent and high volume. There are hundreds of unknown non-stationary variables influenced by complex human interactions, including black swan events. The dominant model style used is a probabilistic hybrid. What this means is that the independent variables are not related to the related variables, like apple falling due to gravity, or our fingers being burned when we touch the fire. That would be a deterministic model. So this borrows strongly from inferential statistics, and the models must calculate uncertainty of the forecast using p-values and confidence intervals due to inherent randomness in the relationship. The best approaches used are advanced AI and deep learning, transformers, LLMs, and RNNs. There are various kinds of metrics used to measure errors. Here, F1 score or AUC is used rather than R square. The second type of problems that applied statistics solve are the low chaos and high stake. So like in the earlier types of problems, the stake is high but the complexity is low, meaning that the number of X factors is known or of low volume. The factors are physically known, for example in metallurgy and drug half-life. Multivariate modeling would be enough. Examples are in medicine, infrastructure safety, financial solvency risk. In those fields, precision is mandatory, and the outcomes are reviewed at the government or international level itself. Nobody wants an engineering failure or wrong clinical dosages. The fourth type of problem that applied statistics provides prediction to are the high chaos, low stake types. It's like going to the astrologer and asking him, will I get married, or when will I get married? Will I get a promotion or will I not get a promotion? Yes, today an LLM or AI can easily do that job of oracle. You should try it. On a more serious note, this type of problem includes finding the likelihood or probability that they will be clicked through the digital ad that you placed. So whereas the dominant model in the earlier types of problem was deterministic given the scientific physical nature of the problems, like in engineering and medicine, the dominant model in the third type of problem, which has very high chaos, is probabilistic. It means that nothing is definite and fixed. It's obvious, isn't it? How can there be fixed equation to determine whether you're going to get married and when? Finally, the fourth type of problem applied statistics solves are the low chaos and low stake ones. It's about predicting stable, repetitive, routine events to improve operational efficiency, like inventory and common maintenance. Lots of AI companies provide this service for various companies. It helps them manage logistic for traffic. imagine DHL not having one of those predictive models. How would they plan the day with millions of parcels in the air? It's also used for inventory management for a large organization to decide how much to stock, when to reorder, and so on. It's also used for routine machine maintenance. What is the probability that a certain machine will break down based on the way it is being used now? Before there were just sets of rules, but now we have machines to do the predictions, so why not be more accurate? At the same time, it's more economical. Why replace the parts every 6 months when the machine tells us it can be replaced this time in the 8th month, but we had replaced it in the 6th month last time. Next time it could be the 12th month or the 4th month. Let the machine predict. So this type of problem use mostly deterministic model, because most of the variables are known and they are stable enough to deliver a single actionable prediction. So that's it. You have come at the edge of this gigantic confluence for which I find difficult to find words even as a writer. For me, having found this place in the space of knowledge has been equivalent to striking gold, because my work is mainly related to research, even though I'm not in the academic field. But through this section I've democratized applied statistics. I have lowered the bar for entry to the minimum. I tried to inspire you, and I hope I did. I loved watching MMA more than any of the 4 individual martial arts that it combines. I love applied statistics more than any of the 4 subjects it combines. Finally, I hope that I was able to transmit some of my fervor, awe, and passion to you through this section.